In this lesson, we're going to learn how to test a claim about a mean when a standard deviation is unknown. So when we test claims about a population mean U when standard deviation sigma is not known, there are several requirements. First, the sample needs to be a simple random sample. The value of the population standard deviation sigma is also not known. And third, either or both of the following conditions must be satisfied. The population must be either normally distributed or the sample size must be greater than 30. The answers that you'll see in the back of the textbook will always list p-values. However, we will not be finding p-values because we will need a TI-83 calculator or a statistical computer program to compute these. The test statistic for testing a claim about a mean with an unknown population standard deviation is t equals x bar minus mu sub x bar divided by s divided by the square root of n. Here's our first example. This will involve a claim involving equality. In an analysis involving the usefulness of pennies, the cents portions of 100 randomly selected credit charges were recorded. The sample has a mean of 47.6 cents and a standard deviation of 33.5 cents. If the amounts from 0 cents to 99 cents are all equally likely, the mean is expected to be 49.5 cents. Use a 0.01 significance level to test the claim that the sample is from a population with a mean equal to 49.5 cents. What does the result suggest about the cents portions of credit card charges? So let's look at the numbers in this problem. First, n equals 100 because we have a total of 100 in our sample. Second, x bar is 47.6 because that is the sample mean. Third, S is the sample standard deviation of 33.5 cents. And the significance level always gives us alpha. So alpha is 0.01. And then finally, the claim gives us the mu sub x bar. Since we're testing a claim that the sample is from a population with a mean equal to 49.5 cents, that would be mu sub x bar. The first step is to address the claim and the hypotheses for our test. So the claim is mu equals 49.5. Since the claim involves equality, we know this is a two-tailed test. Since we're using student t distribution, because our test statistic is a t and not a z, we'll be using table A3. Make sure that you identify if it's two tails or one tails because that will also affect the appropriate critical value. Now for the hypotheses. The null hypothesis is mu equals 49.5. The null is always equal. And the alternative is either going to match the claim or be the opposite of equal. So our null hypothesis is equal and our claim is going to be not equal. Now let's set up the test statistic. So we have t equals sample mean minus claim mean. So we have 47.6 minus 49.5 divided by sample standard deviation, and that's divided by the square root of 100. So you can enter this in separately in your calculators, or you can enter it in one step as well. Always round t to 3 decimal places. So we get negative 0.567. Now for the critical value. Since we were told that we have 100 in our sample, and since we're also using student t distribution, we have to find the degrees of freedom. The degrees of freedom is always one less than your total in the sample. So we have 99 degrees of freedom. So in our table, we're going to try to go to the 99th row. Also, alpha is 0.01, which means that that's the area in two tails because that was a two-tailed test. So let's go ahead and look at Table A3 to see how to look up the appropriate test statistic. So in Table A3, we know that we're looking for the 99th row. Now notice that there is no 99th row, so we're going to have to go to row 100. And alpha was 0.01, that was our significance level in two tails because it's a two-tailed test. So you have 2.01, so make sure that you're using the correct one, whether it's a one-tailed test or two-tailed test. So for this we want to look at the test statistic or the critical value in the first column. So that's going to be 2.626. Notice these are always positive, but when we're dealing with critical values, you can have positive or negative depending on the tails and if it's a two-tailed test. So let's go back to the PowerPoint. So we've established that the critical value is going to be positive and negative 2.626 because this was a two-tailed test. So let's draw a picture, and the picture is going to help us determine whether we need to reject the null or fail to reject the null. And when we draw this picture, we're doing the traditional method or the critical value method for the procedure and not the p-value. Okay, so what we want to do is sketch where the critical values are going to go. So we have critical value 2.626, and then we have the negative 2.626. And then the tails are going to be the critical regions. So if our test statistic falls in those tails, then we decide to reject the null. If it doesn't, we decide to fail to reject the null. On a previous slide, we calculated the test statistic to be negative 0.567. So negative 0.5 would be a little bit to the left of 0. So we plot that, and we could see that that is falling in the region where we would fail to reject the null. So here's the conclusion. We failed to reject the null since the test statistic does not land in the critical region. So there is not sufficient evidence to warrant rejection of the claim that the mean is 49.5 cents. The cents portion of check amounts are such that the values from 0 cents to 99 cents are equally likely. To help you with the wording of your conclusion, make sure that you're using the flow chart that we discussed for this chapter. So you look at, does the claim involve equality, and this one did, and did you reject the null? And no, we did not. We failed to reject the null. So that helps you set up the appropriate wording. Here's example 2, another claim involving equality. Data set 13 in the back of the book lists measured voltage amounts obtained from the author's backup UPS. According to the manufacturer, the normal output voltage is 120 volts. The 40 measured voltage amounts in the data set have a mean of 123.59 volts and a standard deviation of 0.31 volt. Use a 0.05 significance level to test the claim that the sample is from a population with a mean equal to 120 volts. So let's identify the numbers in the problem and how they'll be used in our test statistic formula and for setting up the claim and hypotheses. So the total in our sample gives us n is 40. The sample mean is x bar, and that's 123.59. The sample standard deviation is 0.31, and the significance level gives us alpha. Alpha is 0.05. Finally, the value that we're testing in our claim is 120, so that would be mu sub x bar. So our claim is mu equals 120 because we are showing that the mean is equal to 120 volts. Since the claim involves equality, this is a two-tailed test. So when we look up our test statistic and critical value in Table A3, we need to make sure that we're looking at the two tails. Our null hypothesis is always equal, so in this case it will match the claim, mu equals 120. That forces the alternate to be not equal. So here's our test statistic. We have t equals sample mean minus claim mean, so 123.59 minus 120, divided by sample standard deviation, divided by square root of n. So we have 0.31 divided by square root of 40. So the test statistic t is 73.242. Always round that to 3 decimals. Now that's a very extreme test statistic that can tell it's very far out in that right side of the tail. So I can already tell right now that's going to land in that critical region when I do my picture. So the critical value, first we need to figure out how many degrees of freedom we are, and so that helps us land on the appropriate row in table A3. So we have 40 in our sample, we subtract 1, and we get 39. So in my table, I want to go to the 39th row in table A3. The area in two tails, so remember this was a claim involving equality, so it's a two-tailed test, and our significance level is going to help us figure out where we want to also go on that table. So I want to go to two-tail area, alpha is 0.05. So if you put that together, you're going to land at 2.023. Since it's a two-tailed test, we say positive and negative. So now let's sketch the standard normal distribution curve, and this is going to help us determine if we fail to reject or reject the null. So I plot 2.023, that's a critical value, and negative 2.023. And then I have these critical regions, which is going to be my rejection region. Now my test statistic that I computed was a very extreme value. It was 73.242. So that definitely lands in this critical region, so I'm going to make the determination to reject the null. So we reject the null because the test statistic falls in the critical region. Now look at your flowchart to help you set up the wording. The original claim did involve equality. Did we reject the null? Yes. So here's how we set up the wording. There is sufficient evidence to warrant rejection of the claim that the mean voltage amount is 120 volts. In our third example, we're going to look at a hypothesis test with a claim involving greater than. A simple random sample of pages from Merriam-Webster's Collegiate Dictionary 11th edition is obtained. Listed below are the numbers of words defined on those pages. Given that this dictionary has 1,459 pages with defined words, the claim that there are more than 70,000 defined words is the same as the claim that the mean number of defined words on a page is greater than 48. Use a 0.05 significance level to test the claim that the mean number of defined words on a page is greater than 48. So in this last sentence here, it says use a 0.05 significance level. So alpha is 0.05. And it says test the claim that the mean number, so I'm going to use mu, is greater than 48. So I have mu greater than 48. So my claim mean is mu sub x bar is 48. So if I back up a little bit, it says the dictionary has 1,459 total pages. And then we look at the statement that they want to know does this result suggest about the claim that there are more than 70,000 defined words? So really this is kind of tied into figuring out what the average number of words is. So I'm not going to use the 70,000. Now what we have down here is a set of, it's a sample where we looked at the number of words on these particular pages. So we have to do some calculations here to figure out what the sample mean is and the sample standard deviation is. Also, if I count these up, there are 10 of them, so n is going to be 10. So we need to set the calculator to 1-bar statistics and enter in the data. So go to your calculator, and however your model works, you need to get it in statistics mode, and you need to clear any previous data. And then you want to calculate. So the Texas Instruments TI-30X2S calculator has a stat bar button on it, and that's your calculate button. You want to figure out what the mean and the standard deviation is. So when you do that, this is what you should get. N is 10, the mean, which is x bar, sample mean, 53.3. And S, or S sub x in most calculators, is 15.66. Okay, so the claim is mu is greater than 48 because we're showing that the mean is greater than 48 words. Now, since the claim involves greater than, this is a one-tailed or a right-tailed test. So make sure you look up area in one tail in table A3. For our hypotheses, we have the null is always equal, so mu equals 48, and the alternate is going to match the claim, mu is greater than 48. So let's set up the test statistic. So t equals sample mean minus claim, so 53.3 minus 48. We divide that by sample standard deviation divided by square root of n, so 15.66 divided by square root of 10. So this gives us a test statistic of 1.074 or 1.070, depending on how you entered this in and if you solved it in separate steps, or if you entered it in all in one step, you'll get a slightly different answer. The critical value then, we have 9 degrees of freedom, so we take 1 away from the total in our sample. So we want to go to the table A3 and we want to go to 9th row. Then area in one tail, because remember it was a greater than, so it's a one-tailed test and alpha was 0.05, so that's going to land at 1.833. Only use the positive value because we're graphing a greater than situation. So let's draw this and figure out if this test statistic lands in the critical region or not. So plot your critical value, which is 1.833. So anything to the right of that is our rejection region. Anything to the left is going to be a fail to reject. Then you plot the test statistic to see where it falls. So from the previous slide, our test statistic was 1.074 or 1.070. So either way, that lands just beyond or to the left of the critical value. So it lands in the failure to reject region. So we're going to conclude that we have to fail to reject the null because the test statistic does not fall in the critical region. And so there is not sufficient evidence to conclude that the mean is greater than 48. So let's look at the wording here. Did the original claim involve equality? No. Did we reject the null? No, we failed. So that lets us set up the wording. There is not sufficient evidence to support the claim that the mean number of defined words on a page is greater than 48. You could also go a step further and say there's not enough evidence to support the claim that there are more than 70,000 words in the dictionary. Now let's look at a hypothesis test for a claim involving less than. The trend of thinner Miss America winners has generated charges that the contest encourages unhealthy diet habits among young women. Listed below are body mass indexes, or BMIs, for recent Miss America winners. Use a 0.01 significance level to test the claim that recent Miss America winners are from a population with a mean BMI less than 20.16, which was the BMI for winners from the 1920s and 1930s. This is going to help us determine if recent winners are significantly different from those in the 20s and 30s. Again, we have sample data that we're going to need to type in the calculator, so clear previous data, and you want to figure out your total data, you want to figure out X-bar and standard deviation. Also from the problem alpha, the significance level is 0.01, and we're testing a claim that recent winners have a mean BMI less than 20.16. So whenever we have a mean, it's mu less than 20.16. So this is a left-tailed test. It's a one-tail. So that's going to all help us when we look up our critical value. So enter the data in, and this is what you should get. We have 10 numbers, so n is 10. X bar, the mean, 18.76. S, or sample standard deviation, is 1.1862. Notice I went out several decimal places because I'm going to be putting this into a formula and I want to be precise. So our claim is mu is less than 20.16. And this is a one-tailed test, so when we're looking up our critical value in table A3, look up area in one tail. For our hypotheses, the null is mu is equal to 20.16, and the alternate is mu is less than 20.16. For the test statistic, t equals x bar minus mu sub x bar, so we start with sample mean and we subtract the claim mean. So we have, let me go back and set that up. So our sample mean that we got was 18.76. And I subtract the claim mean, 20.16, and I divide by sample standard deviation, 1.1862, and that's divided by the square root of n, so n was 10. So if you're typing this in your calculator in one step, which is usually the best way to do it, here's how your entry should appear. You do parentheses around the numerator difference, close the parentheses, do divided by, do parentheses again, and then do 1.1862, divide by, get your square root on there. Normally that comes with parentheses. Type your 10 and double close it and then press equals. So it's always good to type things in one step if you can. Okay, so that's going to give us our test statistic t, and it's going to be negative 3.732. Okay, so now let's look at the critical value for the test. So we have 9 degrees of freedom because we had 10 total in our sample, and the area in one tail at alpha equals 0.01 on the 9th row, so 0.01 one tail, 9th row, gives us 2.821, but I use the negative sign because I'm doing a less than test. Okay, so let's go ahead and set up the picture for this. So I have my critical value, negative 2.821. Anything that falls to the left is going to be a rejection, and anything to the right is a fail. Then we plot our test statistic, which was negative 3.732. Now that is further to the left, so it does fall in the rejection region. So I would make the conclusion that I'm going to reject the null. So reject the null because the test statistic falls in the critical region. There is sufficient evidence to support the claim that mu is less than 20.16. So did we have a claim involving equality? No. Did we reject the null? Yes. So this is the way we word our conclusion. So there is sufficient evidence to support the claim that the population of recent winners has a mean BMI less than 20.16. So this test proves that recent winners are significantly different from those who won in the 20s and 30s.